Okay, linear combination of and 1, 2, 1. Okay, so how do we do this? So Christian, you want to do it on the board? Yeah. Okay. Let's see. Very good. And then what do you do next? Right. No, but tell me just the algorithm and everything. So you're going to do elimination on this.
Oh, yes.
Right. So you're going to do elimination on this matrix. And how do you get the answer to this question?
You see if the last column is a free column.
Right. And if it is a free column, then it is a linear combination. So is everyone completely okay with this? Okay, because elimination does exactly, it answers exactly this question. Is any column a linear combination of the prior columns? We just have to make sure that this follows these two columns, and then elimination will give you the answer. Okay, so good. If the last column is a pivot column, then what happens if the last column turns out to be a pivot column? Right, so then it's not a linear combination. Okay. Okay, so everyone 100% okay with this? Okay, this is another way of asking. Another way of asking the same question. Okay, so it's another way of asking, does this set of equations have a solution? Okay, now there are three linear equations and two unknowns. When you simultaneously solve them, do they have a solution? And how do you simultaneously solve these equations? Same thing, you're going to run elimination on this. Okay, and when you get, if you want the solutions, okay, if you want to know exactly how the last column can be written as a linear combination of the previous columns, okay, then what you would do is like you would run elimination. Yeah, you'll check if the last column is free, then the answer for this is yes or no. But if the answer is yes and you want to find out the exact linear combination, complete elimination algorithm till you get to the reduced row echelon form and just read out the numbers in the last free column, and the numbers correspond to the coefficients of the prior pivot columns. Okay, so any questions with any of these? Okay, and also if there are solutions, how many solutions will be there? So I don't know if there are solutions or not, I haven't solved them, but if there are solutions, how many solutions are going to be there? A unique solution. Why? Because this matrix has no free columns. Okay, how do we know it has no free columns? The second column is not a linear combination of the first. How am I sure? Because this is -1, 0, 1. Any scaling of this should have given me a 0 here. I don't see a 0 here, so it can't be a scaling of the first column. Okay, and since I know it's not a scaling of the first column, both are pivot columns. So I don't know if there is a solution, that we do not know. But if there is a solution, the solution will be unique. Okay, so it could have either 0 solutions or exactly one solution. Okay. Um, any any questions? Okay. Okay. So here is a follow-up question. Instead of 231, where I don't know if there is a solution or not, I don't think there is. But I'm going to take 2 times the second column minus plus the first column. Okay, so 2 minus 1 is 1, 4, 2 plus 1 is 3. Okay, so this one I've got it as 2 times. So remember, this is column 1, column 2, column 3. Okay, so I'm getting this as I'm writing the third column as 2 times column 1, sorry, 2 column 1 plus 2 times column 2, right? So I've kind of made up this column, right? So now I know this is a free column, pivot, pivot, free. Okay, now if I change the order of these columns, what happens? So if I make a new matrix, okay, so I have a new matrix, right? So in this new matrix, okay, I've swapped these two columns. Okay, now in this matrix, how many pivot and free columns are there, and which ones are they? Which ones are pivot columns? Which ones are free columns? Right. So even here, the first two columns are pivot columns and the last column is free. Okay. So this column 143, if I'm looking at this column 143, was a free column here because here it could be written as a linear combination of prior columns. Okay. But when I moved it ahead to the second place, it's no longer a free column because it cannot be written as a linear combination of the previous columns, that is the first column. Okay, so this becomes a pivot column. What about column 3 now here? 1 to 1. We already know that these satisfied so we know that these 3 columns satisfied this equation. Okay, so here 1 to 1 is column 3 minus column 1 divided by 2. Okay, so here this one now will be column 2 minus column 1, 1 half column 2 minus 1 half column 1. Okay, because how do I write this column in terms of these two columns? I just move around so that column 2 comes on one side. Okay, so I can write this as column 3 minus column 1 divided, whole thing divided by 2. Okay, but here the identities have changed, so I have to write it as 1 half the 143 column minus the minus 101 column. Okay, so now the third column no longer this 121 column is no longer a pivot column. It loses it's not giving any more information. Okay, so in all this pivot and free stories, it is always whether a column is giving more information relative to the columns prior to it. So when you swap around the order of columns, the identities of pivot and free columns would change. Okay, they could potentially change, but there is actually one thing that does not change. Okay, what does not change is the number of free columns and the number of pivot columns. That never changes no matter how you rearrange the columns. Okay, you're as long as you're permuting the columns anyway. Okay, the number of free columns and the number of pivot columns will not change. Okay, the identities will change. Some of the pivot columns become free columns. Some of the free columns may become pivot columns. Okay, all that can happen, but the number of free columns and the number of pivot columns do not change. Okay, so just as an exercise, I'm swapping column 2 and column 3 here. how should I multiply this matrix to get that matrix? You need to tell me whether it's on the left or right, and by what matrix. What should I multiply? What should I multiply this matrix with in order to get this matrix? Yeah, you multiply on the right because you're manipulating columns. Anytime you want to manipulate columns in a matrix, you will multiply on the right. Okay, anytime you want to do row operations, you multiply on the left. Okay, so you multiply on the right, that's right. But what's the column? What's the matrix I multiply by? What's the size of the matrix I multiply by? Right, so because this is 3 by 3, product is 3 by 3. So this must have 3 columns. This must have 3 rows because numbers adjacent must be the same. And because the product has 3 columns, this must also have 3 columns. Okay, so it's a 3 by 3 matrix. Okay, now column 1 of the product is same as column 1 of this matrix. So what should go into the first column of this matrix? 100, because it just says 1 times column 1 plus 0 times column 2 plus 0 times column 3. Okay, column 2 of the product is column 3 of this matrix. Okay, so I've just labeled the columns because I've because like I think like some of you are telling me it helps if I label these columns. Now this column 3, okay, has to go to column 2 of the product. How do I manage to do that? So the product second column, okay, happens to be 0 times column 1 plus 0 times column 2 plus 1 times column 3. Okay, so what do I write in the second column here? 0, 0, 1. Okay, it reflects the fact that what I have in the second column of the product is 0 times column 1 plus 0 times column 2 plus 1 times column 3. Okay, and what I have here is 0 times column 1 plus 1 times column 2 plus 0 times column 3. Okay, so what should I write here? Okay, I'm talking exclusively in terms of columns of this matrix. So what I have here, okay, is column 2 here. Okay, so it is 0 times this plus 1 times this plus 0 times this. Okay, so what will I have here? 0, 1, 0. Okay, so any questions? Right, and the other fact that column 3 happens to be column 1 plus 2 times column 2. Okay, the fact that column 3 is column 1 plus 2 times column 2. So this is column 1, column 2, column 3. That can be written in terms of an expression here. Like we say this matrix times some vector equals 0. Okay, what is that vector? Very good. Okay, so here like I can write this as column 1 plus 2 times column 2 minus column 3 is 0. Okay, and so it would be 1, 2 minus 1 gives me the 0 vector. Okay, so does this make sense? Okay, any questions with any of this? right? So we are completely comfortable with this. Okay. So now that's good because in all of this calculation, you were never brute force multiplying any single entry. Okay. And we have written all these matrix equations. We have written all of these equations. We know they are true. You can multiply and check. Uh, but we never actually manually multiplied out anything. Okay. That is what we are always doing with matrix multiplications. Okay. So they mean something. And once you get what they mean, like you can handle them very naturally. Okay. So let's go to a different problem right now. Uh, okay. So a lot of these are uh, repetitions of like some of the things we have been saying, and we are repeating it so many times because they are that important. Okay. And because by this phase, like we should no longer be trying to brute force multiply anything. When you see matrix multiplication, it should be telling you a story. Okay. And so that's when we look at like all these neural network architectures and everything. True, they have non-linearities, but they're almost always based off some linear algebra intuition. Okay. Even the most powerful models today, that you use everywhere, they're called transformers, and they are probably the most linear models we have seen in a long time. Okay. And the reason it works is like when people build all of these, they're not just pulling them out of the proverbial rabbit's hat or magician's hat or something. Okay. They're actually thinking of getting information to flow in specific ways, and that intuition comes from linear algebra. Okay. So let's look at the first problem. Is this correct? So when you have numbers, okay, if A and B were numbers, this would obviously be correct. What if A and B are not numbers? What if they're matrices? Okay, so you have A plus B squared, right? And A plus B squared just means A plus B multiplied by itself. Okay, when you multiply these two matrices out, what should you get? Can anyone multiply them for me? So Ethan, right? So do you want to multiply them out? Yeah. 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 Or do it, no, do it carefully.
Oh, I see. Okay.
Right? So, yeah, the back of it. How would you do this? Yeah. So write it out. Use the distributive law to expand.
Oh, I see. Because
Okay. Yeah. Yeah. And simplify. Okay. Oh, no. Okay. Yeah. Right. Complete what you're writing. Complete what you're writing. Okay. So here, so everything is great. Okay, except in the last step, will the last step hold? Okay. So Ethan, right. So till here is fine. Till here is exactly, we are using the distributive law, which matrices also satisfy. But when you go to, you cannot go from here to here in general. Okay, so because AB and BA are not necessarily the same. Okay, so this is not. Okay, so the last step is not true in general. Okay, so this won't be true. So in general, A plus B squared is A squared plus AB plus BA plus B squared. Okay, and that is how far you can go in general with matrix multiplication. Okay, so it is not equal to the last one. It's not, the last step is not generally true. Okay, so just to, right, so the first one, this equation is not true in general, so it's not correct in general. Okay, now this you know very well. So find the matrix E such that for every 3 by 3 matrix A. Okay, so here, like, the reason I'm doing it here is because I want to bring your attention to, like, how we write math. Okay, so what this says is find the matrix E such that for every 3 by 3 matrix A. Okay, so this means that you need one matrix E, okay, that satisfies this for all matrices A. Okay, you cannot make your matrix E depend on A. Okay, there is, so you specify the matrix E ahead of time, and it should satisfy for all A these two conditions. Row 2 of EA is 2 times row 1 of A plus row 2 of A. Okay, so A is 3 by 3. So let's somebody read it out when I write it. So A has 3 rows. Okay, so I mean, it's also given A is 3 by 3. But for now we are doing row operations. So we want find a matrix, E such that for all A. So what should happen? Row 2 of EA. What are the conditions that are required?
Row 2 EA is 2 times row 1 of A.
So row 1, row 2, and row 3 of A. Okay, 2 times row 1 of A
plus row 2 of
okay, and what else do you need? What else do you need?
A. First and third rows of EA equal the corresponding rows of A.
Okay, so what should be EA? What should be E? Right, so you have done this in elimination. You're going to do row operations. So E multiplies on the left of A. Okay, that's kind of already given to you. And the operation you want to do is first the first row you want to leave unchanged. Okay, what should be in the first row of E? 1 0 0, and you also want to leave the third row of A unchanged. Okay, so what should be the last row of E? 0 0 1. Okay, now only the second row you do something interesting. In the second row of EA, I want to get 2 times row 1 of A plus row 2 of A. So what should I write? 2 1 0. Okay, and this is going to be E. Okay, now this is what we have been doing in elimination. Okay, so it's a repeat of that. just pay attention to the way we write when we say find a matrix E such that for all A, it means there needs to be one matrix E that satisfies that property for every A. Okay, you cannot have your E depend on A. Okay, okay, very good. Uh, right, so I leave these three problems for you because they're kind of repetitions of the problems we already did. So for problem three, let's say you interpret this as the x, y, and z coordinates. I'm asking, so you're looking at the plane of all linear combinations. Okay, so you're looking at every linear combination. So that means you're taking uh, the story is a little different, but the problem is exactly something you have done. Okay, so you're looking at all linear combinations. I'm asking if all points on the x-axis lies on the plane of linear combinations. Okay, so if a point on the x-axis is 1, 0, 0, one point on the x-axis is 1, 0, 0, a general point on the x-axis is something like any number a, 0, 0. Okay, a00 is a generic point on the x-axis. Okay, I'm if uh, asking if all the points on this axis lie on the plane is same as asking does a00 can a00 be written as a linear combination of these two. Okay, so geometrically checking whether a point is in the plane is just like solving the set of equations, or you do you put this matrix, put this column 1, 2, 3, then 3, 2, 1, and add up and put A00 as three columns of your matrix, then do elimination. The last column is free, then it means it can be written as a linear combination. Geometrically, it means that point lies on the plane. Okay, does this make sense? Okay, this is just like a different way to ask exactly the same question. Okay, and the final one is also a question on like just matrix multiplication. So I'll leave you to try out this problem by yourself. Okay, and just let me know what your answers are. Okay. 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 So I want you to write. So you've been doing elimination as a numerical procedure, right? Uh, so uh, okay. So for uh, for each row, actually, I should change the wording a little bit. Uh, yeah. So let's just focus on the first row. I want you to write a 3 by 5 matrix such that the first, second, and fifth columns are pivot columns. The rest are free. Okay. Can you come up with an example like that? Uh, Actually, for this, uh, yeah, so for this, let's do one thing. You can use the AI companion. You can use the AI companion to actually help you with this. Okay. Uh, because I'm also curious, like what answers it gives. Okay. I want you to come up with a matrix, 3 by 5 matrix, such that the first, second, and fifth columns are pivot columns. Okay. Yeah. Oh, yes. Oh, it's still happening? Uh, this should. Oh, I think I know why. Why? Because they are having a meeting right now. Just a second. Let me just. Just one second. Uh, because I think they keep having meetings at 9 a.m. and that this goes. Okay, yeah. So, but in the meanwhile, like let's try to do this without. So, I mean, what is probably happening is like last Friday it happened because at this time they are having like a they are actually having a meeting to fix some of the bugs. So they temporarily take it offline, but they seem to have coincided the meeting with the class, so uh, which they'll bring it online, like if it gets the text. But so in the meanwhile, like, can you give me a 3 by 5 matrix so that the first, second, and fifth columns are pivot columns? Yeah, that's very good. Right. So the thing is, like, you do not want to have the headache of figuring out whether. Okay, so you don't want the headache of figuring out which ones are pivot, which ones are free. Okay, so we are going to pick the pivot columns strategically. So it's very easy for us. And this is a very good option. So 100. Oh, there is maybe a new, just one second, just one second. Oh, yeah. Uh, oh, so they're moving it to a, okay, so this is what is happening. Oh, just go to this site. I think there is another process running in it. Uh, Institute, Institute. Yeah, just go to this and you'll find the companion there. I mean, it's running in a different URL. So what is happening? No. So is it the same thing? Like, let me just confirm because they're trying to keep it running while they do all these changes, but maybe it's not working. So even here, like you're getting the same error. Uh,
Still get the same error.
it just gives a blank line. It just gives a blank line, right? Yeah. So okay. So let them fix it. In the meanwhile, I've texted them. So let's go back to this. Like, so we want a Okay, so we want a 3 by 5 matrix where the first, second, and fifth columns are pivot columns. Okay, so let's write out the pivot columns. Pivot columns should not be linear combinations of any prior columns. Okay, so the first column is like this. What do you want as the second pivot column? Right? That is safe. There is no way this is a linear combination of the previous two. And we don't know the third or the fourth yet. So these we need to make it free. And the fifth column, we want to keep it as a pivot column. So give me another one, 0, 0, 1. Okay. Now these two columns should be free columns, which means these columns should be written as a linear combination of the prior columns. Okay. So give me any choice for them. 1, 1, 0, that was good. And another choice, 0, 0. What do you want to say? 0, 0. 1, 0, 0 will work, but 0, 0, 1 will not work. Okay, because then it becomes a pivot column by itself. Okay, so 1, 0, 0 works. And any way you can write it as a linear combination of these two. Okay, okay, good. So let's go to the and you do the other sections in the same way. Okay, but let's go to the next one, like not this. Where is the window? Let's go to the second problem. So you have a matrix M, right? And oh, what just happened? So M has, what are the sizes of M and N? So IM is a M by M identity matrix, and IN is a N by N identity matrix. Okay, so this is a matrix. So we are seeing blocks of the matrix. Okay, now tell me what should be the size of A and B. How many rows does B have? N, because it must have the same number of rows as the identity matrix on the right. Okay, how many columns does it have? M. Okay, so even though we didn't specify, the size of B is kind of fixed. Okay, what about A? How many rows does A have? How many rows does A have? How many? No, so how many rows should A have? So A covers the same number of rows as this identity matrix. M. And how many columns does A have? Right. Very good. Okay. So now we are going to do elimination. So just imagine in elimination, this is the diagonal identity matrix. So you're going to see this as 1, 0, 0. I mean, there are M rows, or sorry, ones in the diagonal, zeros everywhere else. Okay. This is what the identity matrix is. Okay. Now, in this identity matrix, what is your first pivot? So in this matrix, you're doing elimination on M. Okay. You're doing elimination on M, but where will you find your first pivot? Where will you look for your first pivot? Right. And what do you find there? A 1. Okay. And that's your first pivot. Okay. What would you do after that? Right. So you zero out all entries below the 1. Okay. So that would be, and here in the identity matrix, you have a bunch of zeros. Okay. But below it is the first column of B. Okay. So you would zero out the first column of B. Okay. Using row operations. Now, next, what do? You move to the next column, next row. Okay. What do you find there? That happens to be simply the second diagonal entry. Okay. 1. And so you zero out entries below it. Then same thing, right? So you do, so as you proceed with elimination, okay, one of the things that is happening is that the identity matrix, the first time rows, you're not really changing anything because there are no operations to be done to zero out any entries here. Okay, the changes you're doing are all in the subsequent n rows. Okay, so after you go through the first m columns, what is the matrix that remains? Okay, so tell me like how this might work. Okay, think about it, and Wednesday we'll start with this. We'll see how this works. Okay, uh, okay. So think about this and we'll meet on Wednesday. So one of the things that is nice about elimination and pretty much matrix multiplication, elimination, everything is that so far we have been looking at matrices, we have been looking at numbers and operating on numbers, say, okay, find pivots here and everything. You don't have to. You can actually look into blocks of these matrices and do things in exactly the same way. Still works out. Okay, so here, for example, you want to zero out this matrix. The way you can do it is B times the first m rows minus, I mean, the second block is second block minus B times the first block. Okay, and it will just work out perfectly. Okay, just think about it. Okay, so I'll make sure that the companion gets back online. I think they, once their meeting is done, they should, I mean, it should resolve itself like on Friday. But if not, try to use any of these AI things also to retrieve the answer for this question. Okay, and we'll look at all the explanations on Wednesday. Okay, thank you. Thank you. Thanks. Bye.